Sometimes the greatest breakthroughs come from the most unexpected places. Frank Diesel Rodriguez learned this truth while lying beneath a rusted pickup truck in his cramped garage, surrounded by oil stains and broken dreams. The 52-year-old auto mechanic had spent 30 years fixing everything from lawnmowers to 18-wheelers, but never imagined his calloused hands would one day touch the hull of a spacecraft worth $3 billion. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow, I've saved something extra special for you. His tools were ancient, his workspace cluttered with decades of accumulated parts, and his bank account perpetually empty. Yet when NASA's most advanced deep space probe encountered a catastrophic malfunction that stumped their best engineers, it would be Diesel's unconventional wisdom that saved humanity's most ambitious mission to Jupiter's moons. But what happens when a man who barely finished high school challenges the intellectual elite of aerospace engineering? The morning alarm that jolted Diesel Rodriguez from his restless sleep wasn't digital or melodic. It was the grinding screech of his neighbor's garbage truck backing up, followed by the inevitable crash of aluminum cans hitting pavement. For the past 8 years, that sound had marked the beginning of another day spent beneath the hoods of vehicles that their owners could barely afford to fix. Diesel's modest ranch house sat at the end of Maple Street in Clearwater, Texas, a forgotten pocket of suburbia where the American dream had been downsized to simply making it through another month. The single-story home, with its peeling paint and patched roof, had been his sanctuary since the divorce, the only asset he'd managed to keep when his world collapsed around him. His bedroom walls were covered with faded photographs of his daughter Emma at various ages, from gap-toothed kindergarten portraits to her high school graduation picture. Emma was now 23, pursuing her doctorate in astrophysics at MIT, funded by scholarships she'd earned through sheer determination and her father's unwavering support. Every spare dollar from Diesel's garage had gone toward her education, even when it meant choosing between groceries and utilities. The irony wasn't lost on him that his brilliant daughter studied the mysteries of space while he remained earthbound, wrestling with carburetors and transmission problems. But Emma had inherited more than just his mechanical intuition. She'd developed a profound understanding of how complex systems worked, whether they were internal combustion engines or planetary orbital mechanics. Diesel's workshop occupied the converted garage attached to his house, a cramped space that had become his universe over the past decade. Hand tools hung from pegboards with the precision of a surgeon's instrument tray, each wrench and screwdriver positioned exactly where muscle memory expected to find them. A massive toolbox on wheels dominated one corner, its drawers containing specialized equipment accumulated through years of tackling impossible repair jobs. The workspace told the story of a craftsman who understood that quality work required quality tools, even if those tools had been purchased one at a time over many years. His welding equipment was ancient, but meticulously maintained. His diagnostic computers were outdated but still functional, updated with aftermarket software that extended their capabilities far beyond manufacturer specifications. Most mechanics specialized in specific types of vehicles or systems, but Diesel had never been able to afford such luxury. His reputation in Clearwater was built on his willingness to tackle any mechanical problem, regardless of complexity or obscurity. He'd repaired everything from vintage motorcycles to industrial generators, developing an intuitive understanding of how mechanical systems functioned that transcended formal engineering education. The morning routine was always the same: coffee strong enough to dissolve metal, followed by a careful review of the day's scheduled repairs. Most of his customers were working-class families who depended on their vehicles for employment and basic transportation. Late payments were common, but Diesel had learned to balance compassion with business necessity, often accepting installment plans that larger shops would never consider. His first appointment was Maria Santos, a single mother whose ancient Honda Civic had developed a mysterious vibration that 3 other mechanics had failed to diagnose. The car was worth maybe $2,000, but it represented Maria's ability to get to her job at the hospital and her son to school. For Diesel, every repair was personal, connected to real people whose lives depended on mechanical reliability. The Honda's problem revealed itself after 20 minutes of systematic diagnosis. A worn engine mount had created harmonic resonance that amplified through the chassis at specific RPMs, creating symptoms that mimicked more serious issues. The repair required $40 in parts and 2 hours of labor that Diesel charged at his standard rate, knowing that Maria would pay when she could. Working alone had its advantages. No employees meant no payroll obligations, no personality conflicts, and complete control over quality standards. But it also meant that every aspect of the business rested on Diesel's shoulders. He was the mechanic, bookkeeper, parts purchaser, and customer service representative rolled into one perpetually exhausted individual. The isolation was sometimes overwhelming, especially during slow periods when the silence of the garage amplified his awareness of everything he'd lost. His marriage had ended when Sarah decided that she needed more stability than a small-town mechanic could provide. The divorce had been civil but devastating, leaving Diesel with weekend custody of Emma, and the crushing realization that his life's work wasn't enough to hold his family together. But Emma had chosen to stay close to her father, recognizing something in his approach to problem-solving that complemented her academic studies. Their weekend conversations often focused on mechanical principles that applied to larger systems, from automotive engineering to spacecraft design. Emma would describe the challenges facing space missions while Diesel explained how similar problems were solved in terrestrial vehicles. These discussions had become increasingly frequent as Emma progressed in her doctoral studies, focusing on life support systems for long-duration space missions. Her research involved understanding how complex mechanical and electronic systems could be maintained and repaired in environments where traditional support infrastructure didn't exist. The parallels to Diesel's daily challenges were remarkable, even if the contexts were dramatically different. 1,200 miles away, Dr. Catherine Morrison stood in mission control at Johnson Space Center, watching displays that showed the current status of Artemis 7, humanity's most ambitious deep space mission. The robotic probe had been traveling for 18 months toward Jupiter's moon Europa, carrying instruments designed to search for signs of life beneath the moon's frozen surface. The mission represented the culmination of 15 years of planning and development, incorporating technologies that pushed the boundaries of current engineering capabilities. The spacecraft's advanced ion propulsion system, nuclear power source, and sophisticated scientific instruments made it the most complex robotic explorer ever launched by NASA. Dr. Morrison had been the mission's chief systems engineer since its inception, responsible for ensuring that thousands of components would function reliably during the 4-year journey to Jupiter and subsequent 2-year exploration phase. Her background combined aerospace engineering with practical experience in spacecraft operations, making her one of the most respected professionals in NASA's deep space exploration program. The control room buzzed with quiet intensity as teams of specialists monitored telemetry data streaming back from Artemis 7 across nearly 500 million miles of space. Every system parameter was tracked and analyzed, with automated alerts flagging any deviation from expected performance ranges. The spacecraft's health was literally measured in real time, creating a comprehensive picture of how well humanity's most distant ambassador was performing its mission. But at 2:47 p.m. Eastern Time, everything changed. A cascade of warning alarms filled mission control as telemetry indicated catastrophic failure in the spacecraft's primary thermal management system. The specialized cooling loops that maintained optimal temperatures for sensitive instruments and electronics had suffered what appeared to be multiple simultaneous breakdowns. Without functional thermal control, Artemis 7 would be unable to operate its scientific instruments or even maintain communication with Earth. The spacecraft would effectively become a $3 billion piece of space debris, carrying humanity's best hopes for discovering extraterrestrial life into permanent silence. Dr. Morrison's initial response was methodical, drawing on decades of experience with spacecraft anomalies and system failures. Her team immediately began analyzing telemetry data, looking for patterns that might explain what had gone wrong, and whether any backup systems could compensate for the failures. The thermal management system was one of Artemis Vifata I's most critical components, designed with multiple redundancies and failsafes that should have prevented exactly this type of catastrophic breakdown. The system used advanced heat pipes and radiator panels to dissipate waste heat generated by the spacecraft's instruments and electronics, maintaining temperatures within narrow ranges required for optimal performance. Primary analysis revealed that the failure appeared to involve the heat pipe network, a passive system that used phase-change heat transfer to move thermal energy from hot components to radiator surfaces. The technology was well-established and extremely reliable, making the simultaneous failure of multiple heat pipes almost incomprehensible. Dr. Morrison assembled a crisis response team that included thermal engineers, materials specialists, and mission operations experts. Their task was to understand what had happened to Artemis 7 and determine whether any recovery options existed. The spacecraft's current trajectory would take it past Jupiter within 18 months, making any repair attempts increasingly urgent as communication delays grew longer. The team worked through the night, analyzing every piece of available data and consulting with contractors who had designed and built the thermal management components. Computer simulations attempted to model the failure scenarios that could produce the observed symptoms, but none of the scenarios made complete sense given the system's design specifications and pre-flight testing results. By morning, the situation looked hopeless. The spacecraft's internal temperatures were rising beyond safe operational limits, threatening to damage instruments and electronics that had taken years to develop and calibrate. Mission Control faced the possibility of losing contact with Artemis 7 within days, ending humanity's best chance of exploring Europa for the foreseeable future. Dr. Morrison had overseen dozens of spacecraft missions during her career, but she'd never encountered a problem that seemed so completely intractable. The thermal management system had been tested extensively on Earth, subjected to every conceivable failure mode and environmental condition. Its sudden breakdown in space suggested either a fundamental design flaw that had somehow escaped detection or an unprecedented environmental factor that hadn't been anticipated. The media attention was intense, with space enthusiasts and scientists worldwide following the crisis through NASA's public communications. Artemis 7 had captured public imagination as humanity's most ambitious attempt to search for life beyond Earth, making its potential loss a tragedy that extended far beyond the scientific community. Emma Rodriguez had been following the Artemis 7 mission since its launch, incorporating its technological innovations into her doctoral research on life support systems for crewed deep space missions. When news of the thermal management failure reached MIT's aerospace engineering department, she immediately recognized parallels to problems her father had described in automotive cooling systems. The similarities were striking. Both spacecraft and automobiles generated waste heat that needed to be removed efficiently to prevent component damage. Both used liquid cooling systems with pumps, heat exchangers, and radiator surfaces. Both were vulnerable to blockages, leaks, and component failures that could cascade into system-wide breakdowns. Emma's doctoral advisor, Dr. James Wellington, was a former NASA engineer who maintained close connections with current space missions. His expertise in spacecraft environmental control systems made him a valuable consultant on projects like Artemis 7, though he wasn't directly involved in the current crisis. During their regular advisory meeting, Emma mentioned her father's extensive experience with cooling system failures in automotive applications. Dr. Wellington listened politely, but his expression suggested skepticism about the relevance of terrestrial vehicle repair to advanced spacecraft engineering. The academic world often struggled to appreciate practical experience that hadn't been formalized through traditional educational channels. Dr. Wellington respected Emma's intelligence and research capabilities, but he couldn't see how an auto mechanic's insights could contribute to solving problems that stumped NASA's best engineers. Emma understood the institutional bias against non-academic expertise, but she'd grown up watching her father solve impossible problems through creative thinking and intuitive understanding of mechanical systems. His approach to diagnosis often involved considering factors that formal engineering analysis might overlook, leading to solutions that were elegant in their simplicity. That evening, Emma called her father to discuss the Artemis 7 situation. She described the thermal management failure in technical terms, explaining how the spacecraft's heat pipe network had apparently suffered multiple simultaneous breakdowns that defied conventional explanation. Diesel listened with the focused attention he gave to any complex mechanical problem, asking questions that revealed his understanding of heat transfer principles and system integration challenges. His questions weren't academic but practical, focused on understanding how the components actually functioned under real-world conditions. The conversation continued for over an hour, with Emma providing detailed technical specifications while Diesel absorbed information and began forming mental models of how the spacecraft's cooling system operated. His experience with similar systems in terrestrial applications allowed him to visualize potential failure modes that might not be obvious to engineers thinking purely in theoretical terms. By the end of their conversation, Diesel had developed several hypotheses about what might have caused the Artemis 7 thermal management failure. His ideas weren't based on computer simulations or materials analysis, but on intuitive understanding of how complex systems failed in unexpected ways when subjected to environmental stresses they weren't designed to handle. Emma recognized the value of her father's insights, but she also understood the challenges of introducing unconventional ideas into NASA's institutional culture. The space agency operated according to rigorous protocols and hierarchical decision-making processes that didn't easily accommodate input from outside the established aerospace engineering community. The next morning brought more bad news from Mission Control. Artemis V, the One-Eye's internal temperatures had continued rising overnight, now approaching levels that would cause permanent damage to critical instruments. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The spacecraft's advanced spectrometers, designed to analyze Europa's surface composition for signs of biological activity, were particularly vulnerable to thermal damage. Dr. Morrison's crisis team had exhausted conventional solutions, consulting with every available expert and reviewing decades of spacecraft thermal management experience. The consensus was that Artemis V, the One-Eye's failure, represented something unprecedented, possibly involving unknown environmental factors in deep space that hadn't been accounted for in the system's design. The prospect of losing the mission created urgency that transcended normal institutional boundaries. NASA Administrator Patricia Hayes authorized Dr. Morrison to explore any possible solutions, regardless of their source or conventional acceptability. Desperate situations sometimes required desperate measures, even if those measures challenged traditional approaches to spacecraft engineering. Emma saw an opportunity in NASA's growing desperation. She contacted Dr. Wellington and requested permission to present her father's theories about the Artemis 7 failure to relevant NASA personnel. Her proposal was unconventional, but her academic standing and research credentials provided sufficient credibility to warrant consideration. Dr. Wellington's initial response was cautious. He understood the institutional risks of introducing non-traditional perspectives into high-stakes engineering problems, especially when those perspectives came from someone without formal aerospace credentials. But Emma's persistence and the mission's deteriorating situation eventually convinced him to make informal inquiries with his NASA contacts. The response was predictably skeptical. NASA's thermal engineers had already consulted with leading experts from academia and industry, exploring every conventional approach to understanding and potentially resolving the spacecraft's problems. The suggestion that an auto mechanic might contribute useful insights seemed almost insulting to professionals who had dedicated their careers to spacecraft engineering. But Dr. Morrison's desperation was overriding institutional pride. She agreed to a brief consultation, primarily as a courtesy to Dr. Wellington, rather than from any expectation that useful insights would emerge. The conversation would be informal, conducted via video conference to minimize disruption to ongoing crisis response efforts. Emma spent the evening preparing her father for what would likely be a hostile audience of highly educated engineers who questioned his relevance to their problems. She coached him on technical terminology and formal presentation style, though she knew that his greatest strength lay in informal problem-solving rather than academic discourse. Diesel approached the upcoming NASA consultation with the same methodical preparation he brought to any complex repair job. He studied the technical specifications Emma had provided, creating mental models of how the spacecraft's thermal management system functioned and where potential failure points might exist. His analysis didn't rely on computer simulations or theoretical calculations, but on pattern recognition developed through 30 years of diagnosing mechanical failures. He identified several scenarios that could produce the symptoms NASA was observing, scenarios that might not be obvious to engineers thinking purely in terms of design specifications rather than real-world operational stresses. The video conference was scheduled for the following afternoon, giving Diesel 12 hours to refine his hypotheses and prepare for what would undoubtedly be the most important technical discussion of his life. The stakes couldn't be higher. Humanity's best chance of discovering life beyond Earth hung in the balance, and somehow his insights might make the difference between mission success and catastrophic failure. As Diesel sat in his cluttered garage that evening, surrounded by the tools and equipment that had defined his professional life, he never could have imagined that his experience fixing broken cars would become relevant to saving humanity's most ambitious space mission. But sometimes the most unlikely connections produced the most remarkable results. The video conference began promptly at 2 p.m. Central Time, with Diesel seated uncomfortably in front of Emma's laptop at his kitchen table. The screen displayed a conference room at Johnson Space Center filled with NASA engineers whose expressions ranged from polite skepticism to barely concealed impatience. Dr. Morrison led the introductions, maintaining professional courtesy while making it clear that this consultation was being conducted primarily as a favor to Dr. Wellington. The thermal engineering team members introduced themselves with titles and credentials that emphasized their expertise in spacecraft systems and advanced heat transfer technologies. Diesel's introduction was considerably simpler. Frank Rodriguez, 30 years experience in automotive repair, specializing in complex diagnostic problems. No advanced degrees, no publications, no formal credentials that would impress the assembled PhDs and professional engineers. The presentation of Artemis V1I's thermal management failure consumed 15 minutes, with detailed technical explanations of heat pipe technology, radiator panel design, and the telemetry data indicating catastrophic system breakdown. The NASA engineers spoke in the precise language of formal engineering analysis, referencing specifications and performance parameters with academic precision. When they finished, Dr. Morrison politely asked if Diesel had any questions about the spacecraft's thermal management system or the failure symptoms they described. Her tone suggested that she expected a brief exchange before concluding what was clearly viewed as an unproductive consultation. Diesel's first question surprised them with its specificity. He asked about the spacecraft's attitude control system, and whether thermal management failures had coincided with any changes in the vehicle's orientation relative to the sun. The question revealed understanding of how spacecraft thermal environments were affected by solar exposure angles and shadowing patterns. His second question focused on the timing of the failures relative to the spacecraft's trajectory and distance from Earth. Diesel wanted to know whether the problems had begun during specific phases of the mission or in response to particular environmental conditions the spacecraft had encountered. The NASA engineers exchanged glances that conveyed their surprise at the relevance and sophistication of Diesel's questions. His inquiries weren't random or uninformed, but targeted toward understanding specific aspects of the spacecraft's operational environment that could influence thermal management performance. Dr. Morrison answered both questions with detailed technical information, providing telemetry data and mission timeline details that most consultants wouldn't have access to or understand. Diesel absorbed the information with the focused attention of someone processing complex diagnostic data, asking follow-up questions that demonstrated growing understanding of the spacecraft situation. After 20 minutes of technical exchange, Diesel presented his hypothesis about what had caused the Artemis 7 thermal management failure. His explanation wasn't based on computer models or materials analysis, but on pattern recognition from similar failures he'd encountered in terrestrial cooling systems. The spacecraft's heat pipes, he suggested, hadn't failed due to manufacturing defects or design inadequacies. Instead, they'd been compromised by microscopic debris that had accumulated over months of interplanetary travel, gradually blocking the internal passages that allowed working fluid to circulate effectively. The debris wasn't large enough to be detected by conventional diagnostic methods, but its cumulative effect had reached a critical threshold that triggered cascading failures throughout the thermal management network. The problem was similar to cooling system blockages in automotive applications, where gradual accumulation of contaminants eventually caused catastrophic overheating. Diesel's explanation accounted for several puzzling aspects of the Artemis 7 failure that had frustrated NASA's analysis efforts. The gradual onset of symptoms, the apparent randomness of which components failed first, and the system's inability to recover through backup procedures all made sense if microscopic blockages were preventing heat pipes from functioning properly. The NASA engineers listened with growing attention as Diesel described how similar problems were diagnosed and resolved in automotive applications. His approach involved understanding the failure mechanism rather than simply replacing failed components, leading to solutions that addressed root causes rather than symptoms. Dr. Morrison found herself taking detailed notes, recognizing that Diesel's hypothesis offered the first coherent explanation for Artemis 5-1I's thermal management problems that accounted for all observed symptoms. His automotive experience had provided insights into failure modes that spacecraft engineers might not have considered, despite their sophisticated understanding of heat transfer theory. The conference room fell silent as NASA's thermal engineering team processed what they'd just heard. Diesel's explanation wasn't just plausible, it was elegant in its simplicity and consistent with everything they knew about the spacecraft's condition. More importantly, it suggested potential solutions that might allow Artemis 7 to recover functionality. If microscopic debris was blocking the heat pipes, the solution might involve techniques for clearing those blockages or bypassing compromised sections of the thermal management network. Diesel described several approaches that had proven effective in automotive applications, techniques that could potentially be adapted for spacecraft use. The most promising approach involved using the spacecraft's attitude control system to create thermal cycling that might dislodge accumulated debris. By alternately exposing different sections of the thermal management system to solar heating and deep space cooling, it might be possible to create pressure variations that would clear blocked passages. Dr. Morrison immediately recognized the potential of this approach. Artemis Vive 1I's attitude control system was still functional, allowing precise control over the spacecraft's orientation and thermal environment. If Diesel's diagnosis was correct, carefully orchestrated thermal cycling might restore heat pipe functionality without requiring any hardware modifications. The NASA team began developing implementation plans before the video conference had even concluded. Thermal models would need to be created to determine optimal cycling parameters. Mission planning software would need to calculate attitude control sequences that maximized thermal variation while maintaining communication with Earth. Diesel watched the transformation with quiet satisfaction, recognizing the moment when skeptical experts became convinced that his insights were valuable. The NASA engineers were now speaking his language, discussing practical problem-solving approaches rather than theoretical analysis. They'd accepted him as a colleague rather than dismissing him as an irrelevant outsider. The conference concluded with Dr. Morrison expressing genuine gratitude for Diesel's contribution and requesting his availability for follow-up consultations as the recovery effort progressed. His insights had provided the breakthrough that NASA's crisis team needed, transforming an apparently hopeless situation into a solvable engineering problem. As the video connection ended, Diesel sat in his kitchen feeling simultaneously exhausted and exhilarated. The past 2 hours had been unlike anything in his previous experience, requiring him to explain complex technical concepts to some of the world's most sophisticated engineers while defending unconventional ideas against institutional skepticism. Emma had watched the entire conference from MIT, following the technical discussion while observing her father's interaction with NASA's engineering team. She'd seen him transform from a local auto mechanic into a respected consultant whose insights were valued by the world's premier space agency. The call from Dr. Morrison came 3 hours later. NASA's preliminary analysis suggested that Diesel's debris blockage hypothesis was not only plausible but highly probable. Computer simulations indicated that thermal cycling using attitude control maneuvers could indeed create conditions that might clear blocked heat pipe passages. More importantly, the NASA team wanted Diesel's continued involvement in developing and implementing the recovery procedures. His practical experience with similar problems could prove invaluable as they adapted automotive repair techniques for spacecraft applications. The invitation represented something unprecedented in NASA's institutional history. Never before had an auto mechanic been formally consulted on a critical spacecraft engineering problem, much less asked to participate in solution development. But desperate circumstances had created opportunities that wouldn't have existed under normal conditions. Diesel accepted the invitation without hesitation, understanding that this might be the most important work of his life. The little girl who had once dreamed of becoming an astronaut was now studying astrophysics at MIT, and her father was helping to save humanity's most ambitious space mission. Sometimes dreams were fulfilled in ways that no one could have predicted. The recovery effort would begin within 48 hours, as soon as NASA's mission planning team could develop detailed procedures for the thermal cycling approach. Artemis V1I's internal temperatures were still rising, making every hour critical for preserving the spacecraft's scientific instruments and communication systems. But for the first time since the crisis began, Mission Control had reason for optimism. The breakthrough had come from an unexpected source, proving that expertise existed in places that traditional institutions might never have thought to look. A grease-stained mechanic from Texas had provided insights that Harvard PhDs had missed, demonstrating that practical experience could complement theoretical knowledge in remarkable ways. As evening settled over Clearwater, Diesel stood in his garage looking at the familiar tools and equipment that had defined his professional identity for 3 decades. Tomorrow, those same diagnostic skills would be applied to the most complex machine humanity had ever sent into deep space. The auto mechanic who had always fixed whatever was broken was about to attempt the most ambitious repair job of his life. Mission control at Johnson Space Center had been transformed into a war room where sleep-deprived engineers worked around the clock to implement Diesel's unprecedented recovery plan. The massive displays that normally showed routine telemetry data now tracked every degree of temperature change aboard Artemis 7 as the spacecraft executed the most unconventional repair procedure in NASA's history. Dr. Morrison had barely left the control room in 48 hours, surviving on coffee and determination while coordinating between thermal engineers, mission planners, and the unlikely consultant who had become central to their recovery efforts. The institutional resistance to Diesel's involvement had evaporated, as his insights proved increasingly valuable, replaced by desperate hope that automotive repair wisdom could save a $3 billion space mission. The thermal cycling procedure required precise choreography between Artemis VYI's attitude control system and its remaining functional components. The spacecraft needed to rotate through specific orientations that would alternately expose different sections of the thermal management network to direct solar radiation and the absolute cold of deep space. The temperature variations would create pressure pulses inside the heat pipes that might dislodge the microscopic debris Diesel believed was blocking internal passages. Each cycle took 6 hours to complete, during which Mission Control monitored hundreds of telemetry parameters while tracking incremental changes in thermal performance. The process was painstakingly slow, requiring patience that conflicted with the urgency created by steadily rising internal temperatures that threatened permanent damage to critical instruments. Diesel had established a temporary workspace in his garage where he could participate in real-time consultations while maintaining his regular automotive repair schedule. His laptop displayed the same telemetry feeds that NASA engineers were monitoring, allowing him to track the spacecraft's condition and provide guidance on adjustments to the recovery procedures. The arrangement was surreal. A small-town mechanic was simultaneously fixing transmission problems for local customers while advising NASA on spacecraft thermal management issues. His ability to shift mental gears between terrestrial and space-based engineering challenges demonstrated the universality of diagnostic thinking that transcended specific applications. Emma had taken leave from her doctoral studies to serve as liaison between her father and NASA's engineering teams. Her academic credentials provided institutional credibility, while her intimate understanding of Diesel's thought processes allowed her to translate between informal automotive wisdom and formal aerospace engineering language. The collaboration had evolved into something unprecedented in NASA's bureaucratic culture. Diesel's practical insights were being integrated with sophisticated computer modeling and systems analysis, creating hybrid solutions that combined intuitive problem-solving with rigorous scientific validation. The partnership was proving more effective than either approach could have achieved independently. The first signs of improvement appeared during the third thermal cycle. Telemetry indicated slight decreases in some internal temperatures, suggesting that heat transfer capacity was beginning to recover in sections of the thermal management network. The changes were marginal, barely detectable within normal measurement uncertainties, but they represented the first positive indicator since the crisis began. Dr. Morrison's announcement of the preliminary improvements was met with cautious optimism in mission control. Decades of spacecraft operations had taught NASA personnel that apparent successes could quickly reverse into new failures, making premature celebration dangerous for both morale and decision-making. But the temperature decreases were consistent with Diesel's predictions about how blocked heat pipes would respond to thermal cycling. The media attention surrounding the unprecedented collaboration had grown exponentially as news outlets discovered the human interest story of a Texas auto mechanic helping NASA save a crucial space mission. Television crews had begun gathering outside Diesel's modest home, transforming the quiet residential street into an impromptu media circus. Diesel handled the attention with characteristic humility, deflecting credit toward NASA's engineering teams while emphasizing that his contributions were simply applications of universal mechanical principles. His interviews revealed a thoughtful individual whose practical wisdom complemented rather than challenged formal scientific expertise. The publicity was creating complications for NASA's institutional image management. Public relations officials struggled to explain how an auto mechanic had identified solutions that escaped their most qualified engineers, while simultaneously maintaining confidence in the agency's technical capabilities and professional standards. Dr. Morrison found herself defending the collaboration during press briefings that focused more on organizational politics than engineering solutions. She emphasized that Diesel's insights represented valuable outside perspectives rather than indictments of NASA's internal expertise, though the distinction was often lost in media coverage that preferred dramatic narratives over technical nuance. The recovery process required continuous refinement, as each thermal cycle provided new data about the spacecraft's condition and response to treatment. Diesel's automotive experience proved invaluable for interpreting subtle changes in system behavior that might indicate progress or reveal new problems requiring different approaches. His ability to recognize patterns in complex diagnostic data impressed NASA engineers who had initially questioned his relevance to spacecraft engineering. Diesel's insights weren't based on theoretical knowledge, but on intuitive understanding of how mechanical systems behaved under stress, providing perspectives that complemented formal analysis methods. The collaboration was also revealing institutional blind spots in NASA's approach to problem-solving. The agency's emphasis on formal credentials and established procedures had created barriers that prevented consideration of unconventional ideas, even when those ideas might offer solutions to otherwise intractable problems. Emma observed these dynamics with the analytical skills of someone trained in both academic research and practical problem-solving. Her doctoral studies had exposed her to the strengths and limitations of institutional science, while her upbringing had demonstrated the value of experiential knowledge that couldn't be captured in textbooks or peer-reviewed publications. The success of her father's involvement was challenging assumptions about expertise and credibility that extended far beyond aerospace engineering. If an auto mechanic could contribute meaningful insights to spacecraft thermal management, what other valuable perspectives were being overlooked by institutions that prioritized formal qualifications over practical capabilities? By the end of the first week, Artemis VI's thermal management system was showing consistent improvement across multiple measurement parameters. Internal temperatures had stabilized and begun decreasing, indicating that heat transfer capacity was recovering as blocked passages were gradually cleared by the thermal cycling procedure. The success was creating new challenges for NASA's crisis management team. Media attention was intensifying as the story of the mechanic saving the space mission captured public imagination. Congressional representatives were asking pointed questions about how NASA's expertise gaps had required outside consultation from someone without formal aerospace credentials. Dr. Morrison was spending increasing amounts of time in meetings with agency administrators who wanted to understand how the situation had developed and what institutional changes might prevent similar embarrassments in the future. The focus on organizational damage control was distracting from ongoing technical work that required her direct involvement. Diesel remained focused on the engineering challenges rather than the political implications of his involvement. His primary concern was ensuring that Artemis VI's recovery continued progressing, and that NASA's teams had all the insights he could provide. The bureaucratic complications were someone else's responsibility to resolve. The spacecraft's gradual improvement allowed Mission Control to begin planning for the restoration of full scientific operations. Instruments that had been shut down to prevent thermal damage could potentially be reactivated once internal temperatures returned to safe operating ranges. The mission's scientific objectives might still be achievable if the recovery continued at its current pace. Emma had become an informal spokesperson for the collaboration, explaining to reporters and academic colleagues how practical experience could complement theoretical knowledge in solving complex engineering problems. Her position as a doctoral candidate in astrophysics provided credibility, while her personal connection to Diesel offered unique insights into the value of experiential expertise. The story was resonating with audiences who appreciated narratives about ordinary people contributing to extraordinary achievements. Diesel's humble background and self-effacing personality made him an appealing figure who represented the potential for anyone to make meaningful contributions regardless of their formal credentials or social status. But the success was also creating pressure for Diesel to capitalize on his newfound fame through book deals, speaking engagements, and consulting opportunities that could transform his modest lifestyle. He was approached by literary agents, television producers, and business development firms who recognized the commercial potential of his story. Diesel's response to these opportunities reflected the same practical wisdom that had made him valuable to NASA. He was willing to share his insights and experiences, but only in ways that genuinely helped people, rather than simply generating profit from temporary celebrity status. His priority remained supporting his daughter's education and maintaining the automotive repair business that provided his livelihood. The second week of thermal cycling produced even more encouraging results. Artemis VI's heat pipe network was approaching normal operating capacity, with temperature distributions returning to patterns that matched pre-failure baselines. The recovery was exceeding NASA's most optimistic projections, suggesting that Diesel's diagnosis and treatment approach had been remarkably accurate. Mission Control began preparing for the gradual reactivation of scientific instruments that had been dormant since the thermal management crisis began. The process would require careful coordination to ensure that additional heat loads didn't overwhelm the recovering thermal system or trigger new failures in components that had been stressed by prolonged exposure to excessive temperatures. Dr. Morrison's confidence in the recovery was growing, but she maintained the cautious optimism that came from decades of experience with spacecraft operations. Success in space exploration was always temporary and conditional, subject to new failures and unexpected challenges that could emerge without warning. The institutional impact of Diesel's involvement was becoming clearer as NASA administrators conducted internal reviews of the crisis response and decision-making processes. The agency's initial reluctance to consider outside perspectives had nearly cost them the mission, highlighting the need for more flexible approaches to problem-solving that could incorporate unconventional expertise when traditional methods proved inadequate. The collaboration had also demonstrated the value of interdisciplinary thinking that connected seemingly unrelated fields of expertise. Diesel's automotive experience had provided insights into spacecraft engineering not because the technologies were identical, but because the underlying principles of thermal management and system diagnostics were universal. Emma's role as translator between her father's practical knowledge and NASA's formal engineering culture had proven crucial for making the collaboration effective. Her ability to communicate in both languages allowed ideas to flow in both directions, enriching NASA's understanding while helping Diesel appreciate the sophisticated analysis methods that complemented his intuitive problem-solving approach. The media coverage was evolving from simple human interest stories toward more substantive discussions about expertise, institutional learning, and the value of diverse perspectives in solving complex problems. Academic researchers were beginning to study the collaboration as an example of how organizations could benefit from engaging with unconventional sources of knowledge. Diesel's garage had become an unlikely pilgrimage site for engineers, researchers, and curious visitors who wanted to understand how automotive repair wisdom had saved a space mission. He accommodated the attention graciously, while maintaining his regular work schedule, treating celebrity status as a temporary distraction from his primary responsibilities. The third week brought definitive confirmation that Artemis V5II's thermal management system had recovered full functionality. All heat pipes were operating within normal parameters, internal temperatures had returned to optimal ranges, and the spacecraft was ready to resume its scientific mission toward Europa. Mission Control erupted in celebration as Dr. Morrison announced that the crisis was officially over. 3 weeks of intensive collaboration between NASA engineers and a Texas auto mechanic had achieved what many experts had considered impossible, saving humanity's most ambitious search for extraterrestrial life through innovative problem-solving that transcended traditional institutional boundaries. The success was being hailed as a triumph of creative thinking and collaborative expertise that demonstrated the value of remaining open to unconventional ideas regardless of their source. Diesel's contributions had proven that valuable insights could emerge from unexpected places when organizations were willing to listen and adapt their approaches. But the recovery's completion also marked the beginning of new challenges related to integrating lessons learned from the crisis into NASA's ongoing operations and institutional culture. The agency needed to develop systematic approaches for identifying and incorporating external expertise while maintaining the rigorous standards that ensured mission safety and success. Emma was documenting the collaboration for her doctoral dissertation, analyzing how practical experience and formal education could complement each other in solving complex engineering problems. Her research was contributing to broader discussions about knowledge validation, institutional learning, and the democratization of expertise in technical fields. The scientific community was beginning to recognize that the Artemis 7 recovery represented more than just a successful engineering solution. It demonstrated the value of intellectual humility and collaborative problem-solving that could serve as models for addressing other complex challenges facing humanity. Diesel's involvement in the crisis had transformed him from a small-town mechanic into a symbol of practical wisdom and creative problem-solving. But his response to fame reflected the same values that had made him an effective diagnostic technician, emphasizing substance over publicity and focusing on genuine contributions rather than personal aggrandizement. As Artemis 7 resumed its journey toward Europa with fully functional thermal management systems, Mission Control began planning for the scientific observations that would justify the mission's enormous cost and complexity. The spacecraft's instruments were operating perfectly, ready to search for signs of life beneath Europa's frozen surface. The recovery had created new possibilities for NASA's future missions and institutional approaches. The agency was developing protocols for engaging with external expertise while maintaining appropriate quality control and safety standards. The goal was to capture the benefits of diverse perspectives without compromising the rigorous analysis that space exploration required. Dr. Morrison had been promoted to Director of Mission Operations, with expanded responsibilities that included developing collaborative approaches to complex problem-solving. Her experience managing the Artemis 7 crisis had demonstrated the value of leadership that remained open to unconventional ideas while maintaining focus on mission objectives. The transformation of NASA's culture was proceeding gradually, with institutional momentum that favored established practices over innovative approaches. But the success of Diesel's involvement had created precedents that would make future collaborations more likely and more effective. Emma was completing her doctoral studies with research that had been enriched by her family's unexpected involvement in space exploration. Her dissertation was contributing to academic discussions about knowledge integration and collaborative expertise that extended far beyond aerospace engineering applications. The story of the auto mechanic who helped save NASA's most important space mission was becoming part of the agency's institutional memory, a reminder that expertise could emerge from unexpected sources when organizations remained humble enough to recognize and embrace valuable insights regardless of their origins. Diesel had returned to his regular routine of fixing cars and trucks for Clearwater residents, but his perspective on mechanical problems had been permanently altered by his brief involvement in spacecraft engineering. The universal principles of diagnosis and repair that he'd always understood were now consciously recognized as applicable to the most sophisticated technologies humanity could create. His garage remained cluttered with the same tools and equipment that had defined his professional identity for 3 decades, but the space now held additional significance as the unlikely birthplace of solutions that had saved a $3 billion space mission. The transformation was invisible to casual observers, but profoundly meaningful to anyone who understood the connection between practical wisdom and extraordinary achievement. The collaboration between NASA and a Texas auto mechanic had succeeded in ways that extended far beyond the immediate crisis it was designed to address. It had demonstrated the value of intellectual humility, collaborative problem-solving, and recognition that expertise existed in forms that institutions might not immediately recognize or appreciate. As winter settled over Clearwater, and the daily routines of small-town life resumed their familiar patterns, Diesel continued fixing whatever needed repair with the same dedication and skill that had always characterized his work. But now he understood that the mechanical intuition he'd developed through decades of practical experience connected him to the largest and most ambitious endeavors of human civilization. The auto mechanic who had learned to see beyond immediate symptoms to underlying causes had helped ensure that humanity's search for life in the universe could continue. It was a connection that would have seemed impossible just months earlier, but had proven as real and functional as any mechanical system he'd ever repaired. The lesson wasn't that formal education was unnecessary or that institutional expertise was overvalued, but that the most complex problems often required diverse perspectives and collaborative approaches that honored both theoretical knowledge and practical experience. Diesel's contribution to saving Artemis 7 had demonstrated that wisdom could emerge from any source when organizations remained humble enough to listen and adaptive enough to integrate valuable insights into their decision-making processes. 6 months later, the auditorium at Johnson Space Center was packed with aerospace engineers, government officials, and media representatives gathered to witness something unprecedented in NASA's 70-year history. Frank Rodriguez, still wearing his trademark work shirt with Diesel's garage embroidered on the pocket, stood at the podium where administrators typically announced new missions and technological breakthroughs. The ceremony marked the official conclusion of the Artemis 7 recovery project and the beginning of what NASA was calling the External Expertise Initiative, a program designed to systematically identify and incorporate unconventional solutions to complex engineering challenges. Diesel's involvement had evolved from emergency consultation to formal partnership, fundamentally changing how the space agency approached problem-solving. The transformation hadn't been easy. Months of bureaucratic resistance, institutional skepticism, and procedural complications had tested everyone's commitment to the collaborative approach that had saved the Europa mission. But the undeniable success of Diesel's thermal management solution had created momentum that overcame traditional barriers to organizational change. Dr. Morrison, now serving as NASA's Director of Collaborative Engineering, introduced Diesel with words that would have seemed impossible just a year earlier. The auto mechanic from Clearwater had become the first recipient of NASA's Distinguished Public Service Medal, awarded to someone without formal aerospace credentials, recognizing contributions that exemplified the agency's evolving commitment to intellectual humility and innovative problem-solving. Diesel's acceptance speech was characteristically modest, emphasizing that his success represented universal principles rather than individual brilliance. Mechanical systems followed the same physical laws whether they powered automobiles or spacecraft, and diagnostic thinking applied equally to terrestrial and space-based technologies. The only difference was the willingness to look beyond conventional assumptions about where expertise resided. The audience included representatives from major aerospace contractors who had initially questioned the wisdom of consulting with someone outside their professional community. Their presence acknowledged that Diesel's insights had proven valuable not just for crisis response, but for ongoing engineering development that could benefit from diverse perspectives and unconventional approaches. Emma sat in the front row, watching her father receive recognition that validated decades of dedication to mechanical excellence. Her doctoral dissertation, now complete, had documented the collaboration as a case study in knowledge integration that challenged traditional assumptions about expertise and institutional learning. Major universities were already incorporating her research into engineering education curricula. The ceremony concluded with the announcement of Diesel's new role as Senior Consulting Engineer for NASA's Deep Space Exploration Program. The position would allow him to maintain his automotive repair business while contributing to spacecraft design and problem-solving efforts that could benefit from his practical experience and diagnostic capabilities. The appointment was part of a broader transformation in NASA's organizational culture that recognized valuable expertise existed in many forms and sources. The agency was developing systematic approaches for identifying and engaging with external knowledge that could complement internal capabilities, creating more robust and innovative solutions to complex engineering challenges. Diesel's first official project involved redesigning thermal management systems for the next generation of interplanetary spacecraft. His automotive experience with cooling system optimization was being integrated with advanced aerospace engineering to create more reliable and maintainable thermal control technologies for long-duration missions. The work required him to spend several days each month at Johnson Space Center, collaborating with engineers whose formal education complemented his practical experience. The partnership had evolved into genuine mutual respect that transcended traditional hierarchies based on credentials and institutional affiliation. The project team included thermal engineers with advanced degrees, materials scientists, and systems integration specialists who brought sophisticated analytical capabilities to the collaboration. Diesel's contributions focused on failure mode analysis, diagnostic procedures, and maintenance considerations that drew on decades of experience with real-world system performance. The integration of diverse expertise was producing design innovations that neither approach could have achieved independently. Formal engineering analysis provided theoretical foundations and performance optimization, while practical experience identified potential problems and maintenance requirements that might not be apparent in computer simulations or laboratory testing. Emma had completed her doctorate and accepted a position with NASA's Advanced Life Support Systems Division, where her research focused on environmental control technologies for crewed missions to Mars and beyond. Her work built on lessons learned from the Artemis 7 collaboration, emphasizing robust design approaches that incorporated both theoretical analysis and practical operational considerations. The family's involvement in space exploration had created opportunities that seemed impossible just years earlier. Diesel's garage remained his primary workplace, but it now hosted regular consultations with aerospace engineers who sought his insights on thermal management, diagnostic procedures, and system reliability issues. The transformation of his professional identity had been gradual but profound. The auto mechanic who had once struggled to pay for his daughter's education was now contributing to humanity's most ambitious exploration efforts, while earning recognition as an innovative engineering consultant whose insights transcended traditional disciplinary boundaries. Artemis 7 had successfully completed its primary mission, conducting detailed surveys of Europa's surface and subsurface ocean that provided compelling evidence for the possibility of extraterrestrial life. The scientific discoveries were possible only because Diesel's diagnostic expertise had saved the mission's thermal management systems, allowing the spacecraft's instruments to function throughout the critical observation period. The success had generated enormous public interest in space exploration, with Diesel's story serving as inspiration for educational programs that emphasized the value of practical skills and creative problem-solving. Schools throughout Texas were incorporating his example into STEM curricula that encouraged students to value both theoretical knowledge and hands-on experience. The media attention had largely subsided, replaced by sustained recognition within professional communities that appreciated the collaboration's long-term implications for engineering practice and organizational learning. Diesel was regularly invited to speak at conferences and universities, where his insights into diagnostic thinking and cross-disciplinary problem-solving were valued by audiences ranging from automotive technicians to aerospace engineers. His presentations consistently emphasized that expertise was developed through dedicated practice and careful observation rather than formal credentials alone. The most valuable insights often emerged from deep understanding of fundamental principles that could be applied across different technological contexts and engineering challenges. The success had also created opportunities for broader impact beyond aerospace applications. Manufacturing companies were consulting with Diesel about diagnostic procedures and reliability optimization. Research institutions were studying his problem-solving approaches as examples of expert performance that transcended specific technical domains. Emma's career had benefited enormously from her unique position as translator between practical experience and formal engineering analysis. Her research contributions were recognized as pioneering work in knowledge integration that had implications for education, organizational learning, and collaborative problem-solving across multiple disciplines. The collaboration with NASA had demonstrated that the most complex challenges often required diverse perspectives that challenged conventional assumptions about expertise and problem-solving approaches. The lesson was being applied to other fields where traditional methods had reached their limitations, and innovative solutions required fresh thinking from unexpected sources. Diesel's garage had become a symbol of practical wisdom and creative problem-solving that inspired visitors from around the world. Engineers, researchers, and students made pilgrimages to Clearwater to understand how automotive repair expertise had contributed to saving a space mission, seeking insights that might apply to their own professional challenges. But the physical space remained fundamentally unchanged. The same tools hung from pegboards in precisely organized arrangements. The same diagnostic equipment occupied corners where it had served decades of automotive repair work. The only visible difference was a framed photograph of Artemis 7 alongside Emma's doctorate diploma, reminders of achievements that had emerged from the intersection of practical experience and theoretical knowledge. The partnership with NASA had evolved into a model for other organizations seeking to incorporate external expertise into their problem-solving processes. Government agencies, research institutions, and private companies were developing similar programs that recognized valuable insights could emerge from sources that traditional hiring practices might overlook. The approach required institutional humility that many organizations found challenging to embrace. Success depended on leaders who could recognize the limitations of internal expertise while maintaining quality standards that ensured safety and effectiveness. The balance was delicate but achievable when organizations prioritized problem-solving over professional pride. Diesel's consulting work had expanded beyond NASA to include other aerospace companies and government agencies that valued his diagnostic capabilities and practical problem-solving approach. His reputation had spread throughout industries that dealt with complex mechanical systems requiring reliable performance under demanding conditions. The income from consulting work had transformed his financial situation, allowing him to upgrade his garage equipment and expand his automotive repair capabilities. But the fundamental character of his work remained unchanged. He continued fixing whatever needed repair with the same dedication and attention to detail that had always defined his professional approach. The transformation had been personal as well as professional. Diesel's confidence had grown through recognition that his skills and insights were valuable in contexts far beyond automotive repair. The validation had come, not through formal credentials, but through demonstrated ability to solve problems that stumped highly educated specialists. Emma's success in aerospace engineering had validated his investment in her education while proving that practical wisdom and formal knowledge could complement each other in remarkable ways. Their collaboration had strengthened their relationship while demonstrating that family support could create opportunities that transcended individual limitations. The story of their partnership had become part of NASA's institutional memory, referenced in training programs and organizational development initiatives that emphasized the value of diverse perspectives and collaborative problem-solving. New employees learned about the auto mechanic who had helped save Artemis 7 as an example of intellectual humility and adaptive thinking. The legacy extended beyond individual achievement to broader questions about how society identified and developed expertise. Diesel's success challenged assumptions about the relationship between formal education and practical capability, suggesting that valuable insights could emerge from sources that traditional institutions might not recognize or appreciate. Educational institutions were beginning to incorporate his example into curricula that emphasized the complementary value of theoretical knowledge and practical experience. Engineering programs were developing partnerships with vocational schools and trade organizations that provided students with hands-on experience to complement their analytical training. The changes were gradual but significant, reflecting growing recognition that complex problems often required diverse approaches that transcended traditional disciplinary boundaries. The most innovative solutions emerged from collaborations that honored both formal analysis and practical wisdom, creating synergies that neither approach could achieve independently. Diesel's involvement in space exploration had also inspired other skilled technicians to consider how their expertise might contribute to challenges beyond their immediate professional domains. Mechanics, electricians, plumbers, and other trades professionals were discovering that their diagnostic skills and practical problem-solving capabilities had broader applications than they had previously recognized. The phenomenon was creating new opportunities for collaboration between academic institutions and vocational communities that had historically operated in separate spheres. Research universities were partnering with community colleges and trade schools to develop programs that integrated theoretical knowledge with practical application. As Diesel stood in his garage on a quiet Tuesday morning, watching sunlight stream through windows that overlooked the street where he had lived for more than a decade, he reflected on the extraordinary journey that had begun with a simple phone call from his daughter. The auto mechanic who had once sketched impossible dreams had helped ensure that humanity's search for life in the universe could continue. The tools surrounding him remained the same instruments that had served decades of automotive repair work, but their significance had been transformed through recognition that mechanical principles were universal. The diagnostic thinking that helped him fix broken cars had proven equally valuable for spacecraft thermal management systems operating hundreds of millions of miles from Earth. His partnership with NASA continued through regular consultations and design reviews that contributed to the next generation of space exploration technologies. The collaboration had matured into professional relationships based on mutual respect and shared commitment to excellence that transcended traditional boundaries between theoretical and practical expertise. Emma's career in aerospace engineering was flourishing through positions that allowed her to apply lessons learned from their collaboration to new challenges in space exploration and environmental control systems. Her research continued contributing to academic understanding of knowledge integration and collaborative problem-solving that had implications far beyond aerospace applications. The impact of their story extended through educational programs, organizational development initiatives, and research projects that used their collaboration as an example of successful integration between different forms of expertise. Universities, government agencies, and private companies were applying lessons learned from the Artemis 7 recovery to their own challenges and opportunities. But perhaps the most important legacy was the demonstration that extraordinary achievements could emerge from ordinary circumstances when people remained open to unconventional ideas and willing to collaborate across traditional boundaries. Diesel's success hadn't required him to abandon his identity as an auto mechanic, but rather to recognize that mechanical expertise was more broadly applicable than he had previously understood. The garage remained his sanctuary and primary workplace, surrounded by the familiar sounds and smells of automotive repair work that had defined his professional life for 3 decades. Customers continued bringing their vehicles for diagnosis and repair, trusting his expertise with problems that other mechanics couldn't solve. The daily routine provided stability and purpose that balanced the excitement of space exploration consulting with the satisfaction of helping neighbors maintain the transportation they depended on for employment and daily activities. Both forms of work involved the same fundamental skills and values, applied to different scales and contexts. As afternoon faded into evening and Diesel completed the final repair of another busy day, he understood that his story was ultimately about the recognition that expertise existed in many forms and sources. The auto mechanic who had helped save NASA's most important space mission had proven that valuable insights could emerge from unexpected places when organizations remained humble enough to listen and adaptive enough to change. The lesson wasn't that formal education was unnecessary or that institutional expertise was overvalued, but that the most complex problems often required diverse perspectives and collaborative approaches that honored both theoretical knowledge and practical experience. Success came from integration rather than competition between different forms of understanding. The grease-stained hands that had once seemed limited to automotive repair had touched the hull of humanity's most ambitious spacecraft, ensuring that the search for life beyond Earth could continue. It was a connection that bridged the gap between everyday work and extraordinary achievement, proving that mechanical wisdom was truly universal. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.